Hello, we are Team Interplanetar, an undergraduate student team from Bangladesh University of Engineering and Technology, presenting the latest iteration of our rover, Prochesta, for the Anatolian Rover Challenge 2024. Team Interplanetar has been representing Bangladesh in different Mars rover competitions around the world since 2011. We started our journey with ARC with our Mongol A version 2 rover. Since then, Team Interplanetar has participated in many rover competitions around the world, such as University Rover Challenge, European Rover Challenge, and IRDC. We took part in the International Planetary Aerial Vehicle Challenge, where we won the Innovation Award. We also achieved the 8th position in ARC 2022.
Our team's workspace is situated within the university's project lab. It serves as our central hub for team meetings and project collaboration. Within this space, each subteam has its designated area, facilitating simultaneous work on different project aspects. Here, we refine design, construct, and test subsystems, and assemble the rover. Additionally, we utilize various workshops for tasks such as laser cutting and bending. For testing purposes, we utilize both the project lab and the open space or playground available on our university campus.
We have made every endeavor to minimize the weight of our rover, and it now weighs approximately 53 kg, including the science payload and communication system. Each wheel weighs around 4 kg, while the suspension and chassis together weigh approximately 14 kg. While the antenna is kept straight relative to the ground, suspension and chassis covers length of 1.05 meter, width of 1 meter, and height about 1.53 meter. We have used wheels of diameter 300 mm. In addition, the communication antenna adds 2.1 kg to the overall weight, and the manipulation system weighs around 9 kg, which may vary slightly depending on the specific end effector required for a given task. The manipulator can reach 1 meter above ground and 100 mm below ground. We have implemented a new science payload comprising drill and drilling platform 4.3 kg almost, scooper and chassis respectively 0.2 and 1.5 kg, where the whole payload is of length 343 mm with 260 mm, along with adjustable height 490 mm to 1.1 meter approximately.
This year, a completely new chassis is designed and manufactured to reduce weight and ensure modularity. The chassis is made of stainless steel square tubes, which is TIG welded, providing strength while being lightweight. It provides more space for electronics, arms, and science payloads.
The suspension is made from stainless steel square tube. This year, we made a modification by shifting the link bar differential from the front of the chassis to under the bottom.
We implemented a 4-wheel rocker suspension mechanism to keep the rover lightweight. Wheels are attached to the rockers on either side of the rover chassis. Bar differential keeps the rover chassis balanced at an average angle between two rockers on either side, which allows the rover to climb over rocks and uneven grounds while minimizing the jerking of chassis, thus protecting sensitive electronic components inside. We tested the rover for traversal in extreme rockery terrain. Our rover can climb steep slopes and traverse through harsh environments. Rover can also drive over sandy grounds.
Our current rover is equipped with in-wheel planetary gear and DC motors with VT7960 DC motor drivers.
This year, we are trying to implement censored BLDC hub motors with open source STM32 motor drivers running FOC algorithm to ensure smooth running and constant torque. These drivers are also capable of giving automotive data for precise autonomous navigation.
For the ARM section, L298 motor drivers are utilized to control DC roll motion and gripper movement motors. We employed a DC worm gear motor for base rotation and linear actuators for shoulder and elbow. BT790 motor drivers are used for actuators. For precise gear movement, heavy-duty servos are utilized in the pitch mechanism. In this PCB, we have chosen Raspberry Pi Pico as the microcontroller board.
This year's science board utilizes an Arduino Mega as local microcontroller chosen for its numerous I/O pins. Coupled with motor drivers, our board can operate two DC motors for the movement of science module and another for auger drill. Servo motors facilitate sample collection by the scooper and rotate the sample storage to separate different samples. Load cells and HX711 load amplifier module are incorporated to measure the collected sample.
Various types of motors and sensors will require different voltage sources, so rather than powering each system with separate sources, we have made a centralized power distribution system which will generate 5 volt, 12 volt, and 24 volt buses. We have also designed our customized PCB in such a manner that it can withstand hundreds of ampere current. Power module has also been used here to get the real-time view of voltage and current, and a high current relay will stop the rover in case of emergency.
We have installed an industry-standard kill switch to cut off the power from the batteries in case of emergency. When pressed, the kill switch cuts the power to all moving parts like arm and wheels. Also, the power consumption of the rover is heavily monitored.
Learning from previous years, we have simplified the arm design, and this lighter design is manufactured using TIG-welded SS square tubes. The 6 degree of freedom arm stands on a tightly integrated worm gearbox run by a DC motor which provides base rotation. This worm gear reduces backlash of previous design.
This year, we have modified the previous end effector by replacing most of the plastic parts with aluminum alloy. This enabled us to make the roll, pitch and yaw mechanism 74% smaller in volume while still maintaining the similar strength. The end effector can push buttons, flip switches, plug in USB. With the 360-degree continuous rolling, we can turn knobs and drive screws with a screwdriver. The arm can pick up objects from the ground, pull ropes, open and close latches and drawers.
For ARC'24, we have designed a compact yet powerful science module which is 34 cm long and 26 cm wide with a 7.5 kg payload capacity. For soil collection, we have auger drilling mechanism capable of extracting soil from the depths of 25 cm. A 2 degree of freedom arm scoops the soil and collects them in a closed container. The containers can rotate to take different samples.
Lightweight aluminum frame minimizes overall weight, while high-strength stainless steel is used in critical guides and moving parts, ensuring smooth operation.
For laboratory tests, we have used color-changing chemical analysis for the detection of organic materials in order to determine the presence or absence of life. Iron from phyllosilicates have been used for justifying our hypothesis. Rock sample analysis will be conducted with the help of 2PI camera. Habitability analysis will be done with the help of temperature, pH, and NPK sensors.
Our rover uses a Z2 stereo camera for obstacle avoidance and air tag detection during autonomous navigation.
This year, we implemented inverse kinematics with the complete advantage of Movit motion planning framework. We created a custom IK-Fast plugin for our 5 degree of freedom arm, which works as the kinematic solver. We also implemented real-time jogging motion of the arm with Movit servo package to help the operator manipulate the arm with a joystick.
We are using a custom user interface connected to ROS to perform manual operations with the rover. The rover operator can manually control various functionalities of the rover using this interface. Additionally, a USB joystick can also be used for navigation and executing pre-programmed operations. We are using WebSockets for streaming the video feed from the rover to the base station with low latency. A separate user interface for the camera feed makes it convenient for the operator to monitor the rover throughout the tasks. We have set up a 2.4 GHz communication link between the base station and the rover using 2 Rocket M2s. We are using a 120° 15 dB sector antenna at the base station and a 13 dB omnidirectional antenna on the rover. These are high-gain antennas that ensure no line-of-sight communication between the base station and the rover for up to 1.5 kilometers. The overall communication system of the rover weighs under 3 kilograms. The base station equipments, including the sector antenna and the additional hardware, weigh under 5 kg. This makes the system portable and easy to assemble.
This year, we are using the Stereolabs Z2 stereo camera for obstacle avoidance and air tag detection for our autonomous navigation. This stereo camera enables the rover to detect nearby argo markers and autonomously traverse to the marker's position. For effective task handling, we have created a unique user interface which is connected to ROS, which includes all manual rover operation functions. Our rover operator may simply control a variety of rover movements by pressing various buttons on the user interface and on the keyboard. The rover sensor data and video feed can also be streamed through the user interface for monitoring purposes.
Here are some demonstrations of our rover performing tasks similar to ARC'24. For the first mission in Mars field, our rover excels in scientific tasks like soil collection, chemical analysis, and sample tube delivery. In the second mission on the far side of the moon, the rover will navigate autonomously between several obstacles with precision. For the third mission on the moon field, the rover efficiently navigates between locations, undertaking maintenance tasks crucial for mining operations, like pick up and transport objects, press keys, operate a joystick, pull ropes, and slide dryers. Lastly, in the fourth mission, the rover maneuvers through the Mars field at night, using rail-sense camera with IR for night vision.
We are grateful to our sponsors and partners for their continuous support. Thank you for watching. See you in ARC.